Welcome. Today we're going to build a toolkit. This isn't for fixing a leaky faucet, though. It's for understanding and predicting pretty much all the motion in the world around us. From the perfect arc of a basketball shot to the orbit of a planet, the physics behind it is, well, it's just so elegant, so powerful, and you'll see, it's surprisingly easy to grasp. When you look at the world, motion can seem kind of chaotic, right? A bouncing ball, a car turning a corner. But the amazing thing about physics is that it gives us this incredibly simple set of tools to describe, to map, and even to predict all this movement with just stunning accuracy. So let's start with the first and most fundamental tool in our kit. It's the one that answers the most basic question you can ask. Where is something right now? Now, in physics, we don't just point and say, oh, it's over there. We get way more precise. We use something called a position vector. Just picture an arrow. It starts at a fixed reference point, we'll call that the origin, and it points directly, no detours, right to our object. Okay, this equation might look a little intense at first glance, but trust me, it's actually super simple. Think of it like a recipe for finding something. The little letters with hats on them, E, J, and K, they're just your directions. Go along the x-axis, the y-axis, and the z-axis. And the x, y, and z in front of them, they just tell you how many steps to take in each of those directions. That's it. It's basically a perfect 3D address for your particle. See, this just breaks down a potentially complicated 3D location into a really simple 3-step process. You're just making 3 separate one-dimensional moves. First, you zip along the x-axis. Then you move parallel to the y. And finally, you head up parallel to the z. That final arrow, that vector, is the straightest, most direct path from where you started to where you ended up. Of course, in the real world, things move. So when an object's position vector changes, we give that change a name, displacement. And here's the thing, it doesn't care about the long, winding road the object might have taken. All it cares about is the straight line change from its starting point to its ending point. And figuring out the displacement is actually incredibly simple. You just take the final position vector and subtract the initial one. That's it. This one little subtraction gives you a brand new vector that perfectly sums up the object's overall change in position. But knowing where something is, that's only part of the story. To really get a handle on motion, we need to talk about how quickly that position is changing. And that brings us to the language of velocity and acceleration. So velocity comes in 2 main flavors. First, you've got average velocity. That's just your total displacement divided by how long it took you. Think about calculating your average speed on a long road trip. But then there's instantaneous velocity. That's what your car's speedometer is showing you at any single moment. It's your velocity right now. Now here's an idea that is absolutely crucial. That instantaneous velocity vector, it always points in the exact direction the object is moving at that precise moment. Picture it like an arrow that's just skimming the surface of the object's path, perfectly lined up with where it's headed at that one single point in time. So what happens if that velocity vector starts to change? Well, that's what we call acceleration. And listen, this is so important. Acceleration is not just speeding up or slowing down. Remember, velocity has a direction. So if you just change your direction, like when you drive around a corner, you are technically accelerating, even if your speed stays exactly the same. This picture really makes the whole thing click. Look, the velocity vector shows us where the object is going right now. But that acceleration vector, that tells us how the velocity is about to change. So for an object moving along a curve, see how that acceleration vector points inward? It's literally pulling the object into the turn, changing its direction. Okay, we've got our tools. Position, displacement, velocity, acceleration. Now let's put them to work on one of the most classic problems in all of physics, the motion of a projectile. This right here, this is the big aha moment for understanding projectile motion. Look really closely. The ball on the left is just dropped straight down. The one on the right is shot out horizontally. But look at their vertical positions. They're falling at the exact same rate. They hit the ground at the same time. This one simple picture proves something incredibly profound. And this is the absolute golden rule for solving these problems. I mean, really let this sink in. The sideways motion and the up and down motion are completely, totally separate. It's like they don't even know the other exists. Gravity only cares about pulling things down. It couldn't care less if that thing is also flying sideways. And you know what that means? It means we can take a tricky 2D problem and just split it in half. We get 2 super simple 1D problems for the price of one. It's a game changer. And here's exactly how we do it. Horizontally, no acceleration. Nothing's pushing or pulling it sideways, so its horizontal velocity is just constant. Vertically, well, that's just good old freefall. The velocity is always changing because of that constant downward pull of gravity's acceleration, which we call g. Two totally separate problems with their own simple set of rules. Okay, now let's see how this incredible principle of independence gives us the power to write out the exact equations that can predict the path of any projectile. It's pretty cool. This table just lays it all out so perfectly. It really shows that separation we've been talking about. The horizontal equations up top are super simple. Position is just velocity times time. But look at the vertical equations below. They all have that little g term in them for gravity's acceleration, because that's the only dimension where gravity gets to play. Now for the magic. If we take those position equations from the last slide and do a little bit of algebraic shuffling to get rid of the time variable, t, we end up with this single equation right here. This gives you the height y for any horizontal position x. And if you remember anything from algebra class, you'll recognize this as the classic equation for a parabola. This is the mathematical proof that the path of any projectile is a perfect parabola. We can even take it a step further and get this really handy formula for the total horizontal distance, or the range, of a projectile. And this little equation, it reveals a pretty famous secret. If you want to get the absolute maximum possible range, you need a launch angle of exactly 45 degrees. So to finish building out our toolkit, let's add two more really powerful concepts for describing motion: uniform circular motion and relative motion. This brings us to a really fascinating, kind of mind-bending point. You can be accelerating even if your speed never ever changes. How? Well, if an object is moving in a circle at a constant speed, its direction is constantly changing, right? And a change in direction is a change in velocity, which means it's accelerating. We call this centripetal acceleration, and it always points directly toward the center of the circle. All right, but what if you're the one who's moving? Let's look at this. We've got Alex, who's just standing still, and Barbara, who's cruising by at a constant speed. Now, if they both measure the velocity of that third car, car P, are they going to get the same number? Nope. Their measurements will be different. But, and this is the really cool part, as long as Barbara isn't hitting the gas or the brakes, they will both agree on the car's acceleration. It's a fantastic reminder that what we measure really does depend on our point of view, our frame of reference. And there you have it. We've just built a physicist's toolkit, from simple vectors that pinpoint a location all the way to equations that can predict the arc of a cannonball. We've basically created a new lens to describe and predict the unbelievably intricate dance of motion that's happening all around us all the time. So I guess the only question left is, what are you going to use it to understand?